Hey guys, today we're going to start Chapter 7, Section 1, Introduction to Differential Equations. So there are some things that I have already filled in for you guys, highlighted some things, and you're going to want to have a calculator handy. First of all, let's talk about what a differential equation is. A differential equation is any equation that involves one or more variables of a function, one or more derivatives of a function. These equations describe relationships that involve rates of change. Here's an example. The population P of your state is growing at an instantaneous rate of 3% of the population per year. So the derivative would be dp dt, the rate at which the population is changing. 0.03p is your 3%. If you don't know a numerical value, like in this first statement, it gave you 3%, use K. So Alex and Tina have a new Maine Coon kitten named King Robert. Robert is gaining weight W at a rate that is inversely proportional, set up a fraction, to his age T in months. So the weight at which it's changing, dW dt, equals K over T, where K is a number value. Your cup of Starbites peppermint coffee is cooling at a rate that is proportional to the difference between the room temperature, TR, and the current temperature, T, of the coffee. Obviously, your coffee is going to be warmer than the room temperature, which is why your T is first. Your K is less than 0, it's negative, because your coffee temperature is decreasing, it is cooling. So D, capital T over D of T is negative K times temperature of the room minus temperature of the coffee minus temperature of the room. The general solution of a first order differential equation represents a family of curves, which we will investigate in this unit. Here is what your differential equation will look like, and we're going to start looking at that on the next example at the top of the next page. What it's asking you to do here is to show that both of these y equals values are valid solutions for this given differential equation. Now, as you can see in the differential equation, you have y prime and y double prime. So we're going to start with y equals 2e to the x. We're going to find y prime, and we're going to find y double prime. And then we're going to take y equals e to the negative 4x, and we're going to find y prime, and we're going to find y double prime. And then over here to the side, we're going to take our differential equation and we're going to plug in those values that we just found to see if they are equal. So those are kind of the steps we're going to follow here for example number 2. So the derivative of 2e to the x is 2e to the x, and the derivative of 2e to the x is 2e to the x. A little more work here. E to the negative 4x, negative 4e to the negative 4x, and then 16e to the negative 4x. So we're going to start with the first one here, 2e to the x plus 3 times 2e to the x. Does it equal 4 times 2e to the x? So we have 2e to the x plus 6e to the x equals 8e to the x. And there's your check. Remember, it's already told you that they're valid. And the question here is to show that they are. 16e to the negative 4x plus 3 times negative 4e to the negative 4x equals 4e to the negative 4x. So 16e to the negative 4x minus 12e to the negative 4x equals 4e to the negative 4x. And there's your check. 16 minus 12 is 4. Now, in example 3, it says determine if the solution, whether the function is a solution. So this one, it only has dy dx. So we're just going to find y prime. So we've got 3 times e to the negative 0.5x times negative 0.5. So negative 1.5 e to the negative 0.5x. All right, so now we're going to substitute. We've got 0.5 times 15 minus, there's your y. So 15 minus y. So that's 0.5. All right, 15 minus 15. Can cancel those out. So negative 3e to negative 0.5x. So multiply those out and you get negative 1.5 e to negative 0.5x. So notice they are the same. So we can say, yes, it is a solution. Find g prime for x cubed minus 5. Plug in 5x plus 4 times y. Sorry, I plugged in the wrong thing. X to the fourth minus 5x times the 4 on the outside over x. I went to plug in the derivative. You got to plug into the original g of x. So you have 5x plus 4x to the fourth minus 20x over x, which is 4x to the fourth minus 15x over x, which is 4x to the third minus 15. 4x to the third minus 15 does not equal, that in a different color. These two are not equal, so it would be no. A function y equals f of t, which satisfies a differential equation, is called a solution. We will be able to find both the general and particular solutions using a variety of techniques in this unit. Now, you will only find a particular solution if it gives you additional information that requires you to plug in a point to find that value. So for the differential equation, dy dx equals 3x squared, find the general solution. So you're going to take the antiderivative of each side. So y equals x cubed plus c. Yes, that one was very, very simple. They will get much more complicated than that. So we have a word problem here on example number 5, but it breaks it down into multiple questions so that it will lead you to your answer. You've been given a summer internship at a winery in the Tuscany region of Italy. Your task each day is to track the rate that red grape juice is being pumped into these large stainless steel vats. The depth y is increasing at a rate proportional to the square root of the depth at a given time. Write a rate equation that would represent this situation. So our depth is changing. So dy dt at a rate proportional to the square root of the depth. So value square root of the depth. Remember, k is going to be a number. When the grape juice reaches a height of 4 inches, the depth of the juice is increasing at a rate of 4 inches per hour. So dy dt is going to equal 4. The rate it's increasing is 4 when y is 4. There's your height. So 4 equals k square root of 4. 4 is 2k, so k is equal to 2. So now we're going to write the differential rate equation using your newfound information. So dy dt equals 2 square root y. Complete the table below for the chosen depths using your differential equation. You notice that the depth of the grape juice is changing does not depend on the amount of time. All right, so if we plug in a 0, we get a 0. If we plug in a 4, 2 times the square root of 4, 2 times 2 is 4. Plug in a 3. Plug in a 9. Square root of 9 is 3. 3 times 2 is 6. Square root of 16 is 4. 4 times 2 is 8. Square root of 25 is 5. 5 times 2 is 10. Square root of 36 is 6. 6 times 2 is 12. Square root of 49 is 7. And 7 times 2 is 14. The vintner needs to know the depth of the juice at any given time. That's why he hired you. So what fact do you need to know in order to find an answer for your boss? There's one thing that we haven't discussed that is very important, and that is the initial amount of grape juice in the vat. Chances are pretty good you're not talking about a brand new vat that has nothing in it. There's gonna be some kind of or some amount of juice in there. So suppose there was 4 inches of juice initially, 4 inches of juice in the vat. In order to estimate the depth after 1 hour, we will assume the rate remains constant for the first hour. How did we arrive at an answer of 8 inches? So they're telling you the answer. Now you have to say how you got it. Use this technique to complete the chart. Okay, so at a depth of 4, the rate is increasing. It's staying the same at 4 inches per hour. That's what it told us initially. So 4 plus 4 equals 8. Now we're going to complete the chart. So we've done it for, initially there were 4. After the first hour, there were 8. So now we're going to use these values. So what we did was this was 0, 4. We added 4 to get 8. Now we're going to add 6 to get 14. And we're going to add 8 to get 22. We're going to add 10 to get 32. And we're going to add 12 to get 44. And we're going to add 14 to get 58. So these values here came directly from the chart that we found here. So we're still on the same set of information. So how many functions would satisfy your differential equation? Infinitely many. You can have a million different answers. So what information determines the particular solution that you find? That initial value. Notice how we were able to create the accurate information based on the specific information that was given about how much was in the vat. So use the data from the second table, part F, and plot this particular solution of the differential equation using a blue colored pencil. Well, here are the points that you will plot based on the table. So go ahead and plot them here. This is called a slope field. Our next section is just on slope fields, how to create them, how to read them, etc. So 0, 4, 1, 8, 2, 14, 3, 22, 4, 32, 5, 44, and 6, 58. And just connect your curve. Notice how your slope field kind of follows your points. That's what slope fields do. And then take a green and plot another function that also represents a particular solution of the differential equation. Remember, unless it gives you a specific value, you have a general solution. This one tells you it wants another particular solution. So that means choose any points that you want to that are going to fit the slope field and that are going to fit your curve. So you just want it to be something that's going to, I know it's kind of hard to think about paralleling a curve, but you want it to just kind of go as the slope field goes in the same direction that the curve would go. And remember why this would be different. This would be different because of the amount initially in your vat. Do you notice a relationship between your graph solutions and the slope field in the background, and explain your thoughts? All right, the slope field looks like small tangent lines at some x value, which is time. These are the rates of how fast the depth of grape juice is changing at a specific time. All right, guys, this concludes section 1. Let me know if you have any questions, and I hope you guys have a great day.